In the last blog post, I had some problems that I wanted to work through. So I was going to talk through the design at a high level now and show you some of the problems and how I overcome those problems to get to the point where the power supply is, I guess, in its final state. I keep on saying that every blog. I get to the final design, then I find something else. Anyway, let's go through it quickly just as a recap. So I've drawn a block diagram here. This is effectively the power supply circuit as I built it. This block in the centre represents the digital control board, so that's the PCB that I built. Very straightforward design, already quite familiar with it now. We've got a DC feeding through a shunt resistor, and here we're sensing the current. Now I'm using a Max 4080 chip, or I have been, and we'll talk a little bit about that later. Into the PNP pass transistor, some kind of minimum load on the regulator output, and then the output, and we're sensing the output voltage here with two resistors, and that's being fed back into the control for feedback. So that's pretty much the circuit as we built it. Now the problem with this is there's actually quite a few problems with it when you start getting down to the real fine detail. Certainly when we're trying to get some good measurements. So same diagram again, except for I've drawn a few things on here that are worth noting. The first thing is when you put a significant load on the output, and I've been working on getting this working to deliver 8 amps. Why? No reason other than that's the range I've got on the current for the DAC. So it seems silly to waste that if the circuit can be made to work. It was originally designed for 5 amps. I'm going to try and make it deliver 8. And in testing, one of the good things about trying to get it to work with high currents is that it shows up these problems more. So what I've done here, around the main current path, so from the rectifier through the top HT line all the way through here to the load, in the actual wires going to the load, and then in the same current return path, what you've effectively got here is resistance. Now, for most part, it's copper, and that resistance is negligible. But there are some things the important things that are worth noting. The one thing to remember is that copper has a positive temperature coefficient. So, depending on temperature, that resistance, as minimal as it will change. And obviously, that resistance becomes more apparent the more current you're drawing through the circuit, or the more current. So at 8 amps, by way of an example, there's a fairly significant voltage differential between this point here and, say, for example, this point here, which is the drop across this resistance. Now, while that may seem negligible, think about this for a second. Assume the voltage drop here is, let's say, 2 millivolts. Well, the 0 volt for the reference circuitry, the circuitry that's actually measuring this voltage here, is now being raised by 2 millivolts, and that causes an error, which is actually turns out to be fairly substantial when you look at the error on the output, because we've got a ×2 gain here. If there's a 2 millivolts drop across here, you see about a 4 millivolt error on the output here, even though the sense resistors are sitting here, and that's simply because the voltage here is actually different to the voltage here. So that's a problem. Now, one of the ways of compensating for that, which is what I'd actually done, is I've wired this right here. In fact, on the prototype design, I've actually got 4 terminals, and the sense resistors are connected to those. And I wired the 0 volts return for the control right here, which actually helped quite a lot. But actually, it still gives errors, and simply because here there's errors, and anyway, it wasn't good enough, and I wasn't really happy with it. So I wanted to address that and sort that out. So that's one thing. The second thing is right here I've drawn a symbol of current. What's happening on the op amp? It's a bipolar op amp, the LT1013, and in order for that input is effectively inside the chip feeding a transistor. So there is a current that flows through this path, which is imposed by the op amp. Now it's actually very insignificant when you it's in the nanoamp range, But actually, when you're measuring voltage here at 1, 2 millivolts at the output, actually that current becomes significant. And what it effectively does is delinearizes the effect of this potential divider. So that's another problem that I wanted to try and resolve. And that offset current that you can see on the front of the op amps, the one solution is to use a picoamp op amp, so you don't get that. I've taken a different approach, and we'll come on to that later. The other thing I found is the max 4080, even under no load conditions, I still get a very small voltage here, very, very small offset, but nonetheless enough to know that to see on the output reading, the current output reading, that as I turn the voltage up here, it has a marginal effect on here, and that's partly due to the current here, partly due to the minimum load. But it's just a bit messy, and I couldn't really solve a lot of those problems. I need to have this load here to make the regulator behave. And the problem with the high side sensing here is that I have to compensate for that in software. And because of the voltage range from 0 through to N, I was thinking about using a constant current source, but it starts getting really complicated. And I thought, well, a simple resistor there. The problem with that is that's not linear. Obviously, it draws more current the more the voltage goes up. Calculating the software gets very complicated, and it's all a bit messy. So I wanted to really think about it again and do something quite different to fix those problems. Before I talk about that, if you recall, one of the problems I've had in the design is not really being able to manage the offsets. When I talk about the offsets, I'm talking about the ability for the rail-to-rail op amps that I'm using to go really truly to 0, and they can't quite make it. So eventually, after a lot of soul searching, I thought, well, at the end of the day, I have to put a split supply in the power supply. But I didn't want to change the original design goal, which was to keep a single supply, or a single AC winding of the transformer to feed it. So I didn't want to have to create complex or expensive transformers, or have to use expensive transformers in order to make this work. So that really left me with one option, which was to generate the negative supply from within the circuitry as it stands. And I had two options. I could get an off-the-shelf DC to DC converter, which they're available. They are quite expensive, the good ones, in the region of a few dollars at least. And it's another item to add to the bill of materials. So I thought I'd try building a charge pump, which is what I've done here. And actually this works very well. So all that's happening here is I've got a spare output on the microcontroller, which is a PWM output. So I'm generating about a 32 kilohertz square wave, 50% duty cycle, feeding that into this 3 transistor circuit here, which is effectively a small amplifier. Or it's actually a logic gate. And the reason why it's done like that is I needed a low impedance source here for the 12 volts. That's being fed into a capacitor, a pair of diodes, and a capacitor, and out of there I get about 11 volts. On the bench, testing this circuit as it stands, I could consistently draw 40 milliamps without anything getting hot or without any undue issues. So 40 milliamps is more than what I need. So this is what the circuit looks like now from the 12 volt supply, which is coming from the high voltage 317, which is regulating down from whatever the main supply is. I'm driving a pair of LM3, a 317 and an LM337, giving me plus or minus 5 volts, nice and clean, or relatively clean. So that's how the supply was built. The components here, the 2 NPN transistors and the PNP transistors, are what I already had in the project, so they really didn't have to add anything to the bill of materials. The diodes here are the Schottky diodes BAS4004 part. So reused everything that I'm already using. Resistor values are pretty much picked from the same resistors already in there. So I haven't really had to add anything to the bill of materials in order to add this piece of circuitry, and it works really well for what it's trying to do. So onto the input. In sensing the input voltage, what I really needed to do was sense the actual voltage across the terminals, and I had to do that in the context that the circuitry doing the sensing is actually tied to the same 0-volt line as the rest of the power supply. And the way to do that is to create a difference amplifier. Now, typically you'll see this will be the third element inside an instrumentation amp, and what it effectively is, it's set up with negative feedback. It's a classic configuration, and what it does here is it measures the voltage across here, and the entire rails, you know, the inputs can swing up and down. That's known as the common mode voltage. So if the op-amp allows a decent common mode swing, then it really doesn't matter where these two lines sit, as long as in terms of DC potential or indeed noise, what it's actually measuring is the difference between the two. Now, typically in an instrumentation amp where high impedance is required, there'll be two buffers here. There'll be two voltage follower buffers, making a classic instrumentation amp. As fortune would have it, in this particular design, the output of the power supply is already very, very low impedance, so there's no requirement to do that. So I've taken advantage of that, and I'm using the fact that the output is low impedance to directly drive this. I'm also doubling up on the fact that this is effectively a divide by 2. So if there's 4 volts read across here, 2 volts exactly will come out of here. And these resistors, these 4 resistors here, make this amp a gain of, or unity gain. Okay, so if there's a volt across here, a volt will come out. These additional 2 resistors make that divide by 2 effectively, or half the voltage. So I can set the gain of the power supply circuit just by changing these 2 resistors. All of these resistors at 0.1%, so they're relatively accurate. However, there are some things to consider here. This is also an LT1013, so I've managed to use the same op-amp that was already in the project, so I don't need to add another component. Originally I was thinking about using a pico amp or something like an AD706. I didn't need to in the end. The LT1013 would do fine. The reason for that is because this is such a low impedance source, so these resistors are relatively low resistance to maintain that. But there is an input offset voltage, there is input offset current, as we've talked about, so current will flow here, and these resistors are, you know, to keep the price reasonable, they're 0.1% accuracy. You go beyond that, you go to 0.001% or 0.05% even, then the price of those resistors starts to go up very steeply. So what I've done here is I've added a simple pot strapped between plus or minus 5 volts. You can see a very high impedance source feeding into a very low impedance resistor, 10 ohms here and at 100k here. And what that does is that gives me a swing across this potential here, at this point here, of about plus or minus 1 millivolt, which is more than enough to compensate and to bring this into balance and effectively null it, set it to 0. Typically on here I'm seeing about 300 microvolts, here, about 300 microvolts to null it, minus 300 microvolts, and that broadly speaking compensates for the fact that there's an input offset voltage of about 150 microvolts on this op-amp. I've drawn this in dots here because while this works perfectly, and that's how I've built the prototype, the thing that's been nagging me is I don't want a trimmer in the design. I want everything either done by software. I don't want a trimmer. I don't want to have to get in there with a screwdriver and tweak it to set it. So I wanted to find an alternative way of doing that, and a way I could do it under software control. So to do that, coming back here, the problem with doing that is, as I mentioned before, we're now in a situation where this op-amp is running on a plus or minus 5 volt supply, and really you have to be able to trim this in either direction, a plus or minus 5 volts. So the problem I've got is I've got a microcontroller. PWM circuit is the obvious solution. I've got a microcontroller which can give me a PWM signal. That's the microcontroller is running at 3.6 volts. So I've got 0 to 3.6 volts square wave, variable duty cycle, and I've somehow got to turn that into a plus or minus 5 volt supply. And again, I didn't want to use custom chips. I didn't want to make anything complicated. I wanted to try and stick with parts that I've already got and in the design, and hopefully keep it as simple as possible. Now, as luck would have it, in the latest design, which you'll see on the blog page, I've actually added a second 4053 chip, and that's really to deal with the switching the output on and off, and you'll see that in the circuit diagram. But in that implementation, I had a spare element, a spare analog switch element. So I've taken advantage of using that. It's very simple. We've got the logic signal coming from the microcontroller, which is a variable mark-based PWM. I'm driving the element switch, and I've set the X0 and X1 inputs to -5 and +5 volts respectively. The common output I'm then feeding through 100K, relatively high impedance, and 0.1 microfarads cap. Should have wrote that in there. So nice, very rudimentary low-pass filter, and into a simple voltage follower, which is half an LM358, which I already had in the design also. So again, I haven't had to add anything to the bill of materials to implement this. The output, as we talked about in the previous one, 100K source into a 10 ohm resistor, and that's what provides the offset voltage of ±1 millivolts. I'll show you that circuit in prototype, because I've built a prototype of that and just verified that it done exactly what I expected it to do, and it works very, very well for something so simple. So that's actually quite a novel circuit, because it deals with level shifting. So this is running on ±5 volts. It deals with, so it takes a 0 to 3 volts input, and it generates a plus or minus voltage on the output. Very simple, nothing complicated. It runs at 30 kilohertz, and does exactly what it needs to do. It works really well. So coming back to the design. So what I've done is, taking those circuits, and I've changed things around quite considerably, as you can see from this page here. So let me talk about some of that. First of all, I wanted to deal with this minimum load regulation without having to add all the complexity of calculating that in software, and also effectively delinearizing the circuit. And really the only way to do that was to move away from high side current sensing and move to low side current sensing. I'll talk about that in a second. With the so that's the first really major change that I've made. So if you now look at the path, the output voltage is here, straight through the pass device, through a protection diode. We'll talk about that in the next review of the design. This effectively stops reverse polarity, and then the other half of that is this diode here, to protect the circuit from having, say, a battery put on the output in the wrong way. So moved away from high side current sensing. That's the first thing. That means that I can put and I'll come on to that in a second. The difference amp circuit that we talked about just a couple of slides ago. Here it is implemented. Very simple. It's strapped right across the input, and that drives the voltage sense. This is the PWM output, and that's circuitry that we've just been through, which is again controlled by the microcontroller. So I've got this all under software control. The low side current sense is actually a lot easier to implement, and it's a lot more robust. The op amp, coming back to this, I had to introduce a second LT1013 op amp, which, as you know, is a dual part. So I had a spare part here. Now, having the Max 4080, which is actually a custom chip, and it's quite expensive, it's about $2, it was actually a very good opportunity, because by removing the Max 4080 and going to a low side current sense, I could use the spare element in this second op amp chip, which is what I've done. And it's very simple. Simply put, the current shunt is down here now in the negative return path, and the op amp is strapped straight across that current sense. So as long as the op amp can swing from 0 to whatever the forward current is, and indeed the reverse, not that the ADC will deal with that, because I've got it working in single polarity, then current sense is actually a lot simpler to implement, and there's no offset. There's absolutely no offset. So without doing anything here, just setting the gain here of ×5, I can, and assuming this is accurate, you know, reasonably accurate current shunt, then I can sense the current and return path. Now, if you read a lot about low side versus high side, there's a lot of recommendation that one should use high side current sensing simply because it's safer. And an example, the main thing is what low side current sensing creates a ground path disturbance, and more importantly, if you've got electronics that are truly zero referenced and this is exposed in any way to the outside world, then by returning current through here instead of through here, the power supply can't sense the current being drawn, so you can get dangerous currents coming out of here. In this design, because it's a complete self-contained module, it's actually perfectly safe to do this, and that's the option I've chosen. Now, the other thing with the current sensor, remember we talked about the minimum load that the regulator needs. Well, something really nice happens by doing this, because what we do here is we put the minimum load on the regulator, but we return it down here, on the other side of the shunt. So this can draw 10 or 12 milliamps off the regulator without dropping any current across here. So that solves that problem as well, makes it much simpler. So it's a really nice solution. By doing the voltage sense here at the end, it compensates automatically for the drop across this diode, and in fact across all the resistance around the circuit. So that's now the new top level design. This is what I've built, and that's working really nicely. So if we look at the same sort of problems that we identified before, with this resistance at high current, voltage drop across this diode, voltage drop here. There's a critical part of the entire circuit, which is this star earth. That's what I'm going to call it here. It's this central point, and it's really, really important that that's kept short and as minimal as possible. But everywhere else where there's resistance, voltage drops, right throughout the circuit is entirely compensated for by this, which means that whatever voltage we set inside here, it's precisely output here, and I'll show you in the video. You'll see that working, and it's working really well because these op amps are running on a plus or minus 5 volt supply. It comes right down to 0 volts and 0 amps. So again, deals with offsets, any offsets that are in there, and it works really, really well. That's as we have it now. Okay, so that's as far as I've got. I'll give you a quick demonstration of the hardware now, built as I've just shown you there, and take it from there. Okay, this is the prototype for the PWM level shift DC generator that I'm going to use to trim the analog to digital converter. I've knocked it up. It's pretty simple. There's a 4053 chip, which I'm using one element of. That's the switch, as I showed in the diagram earlier. There's an op amp. There's a simple RC low-pass filter. Test setup, I'm driving 32 kilohertz square wave into the switch, which is operating the switch, switching between +5 and -5 volts. I've got a scope on the input, another scope channel on the output, and a digital meter hooked up as well, just metering the output. All right, so I'll take you through that now and show you the test setup and see how that, and show you the results I'm getting from this circuit. Setup, power supply here giving me plus or minus 5 volts. Got an arbitrary function generator here running at a 32 kilohertz square wave, set to 50% duty cycle. That's driving the 4053 switch element. The scope is looking at the square wave from the function generator, the input of the 4051. The top trace there is the output. What I've done at the moment, I've set it to AC, and I've turned the gain of the scope right up to 50 millivolts per division. You can see that actually, if you look here, there's about 10 millivolts of noise on there, which actually is mostly switching noise from the badly constructed prototype. That's just showing you now. If you remember on the circuit diagram, the output of this output is actually a DC output, and it's going to be driving through a 100k resistor into a 10 ohm resistor down to ground. So that's a division of 10,000, what that means is that that noise is going to be reduced by 10,000, so it's negligible. I'm not going to worry about it. Just set this back onto DC for a second and bring it down to 2 volts of division. So if I adjust the duty cycle, you'll see that by lowering the duty cycle, lower the voltage. You can see how the meter is reading the actual voltage I'm getting on the output. If I just bring it back up to exactly 50%, and if I just ground the scope, you'll see that that is 0. So you can see that the output swing is going plus and minus. That's taking it up to 80%. Unfortunately, the function generator can only go at plus from 20% to 80% duty cycle. I can't take it to 100%. But on the metered output, if you look at the output, for every 10%, there's approximately almost exactly an increase of 1 volt. So it's actually quite precise, really, considering it's such a basic circuit. That's it. So that's what I'm going to put into the power supply to drive the trim for the input amplifier for the difference amplifiers I showed in the circuit before. So I've made quite a few minor modifications to the latest version of the prototype. I thought I'd just talk you through some of those just so you can see them. The first thing is here I've added another current shunt. This time this is the low side current shunt. And I've removed the Max 4080 chip, which was on here. Over here, this is the second LT1013. There's 2 halves of it. This side over here is the difference amp, as we talked about earlier on, and this side over here is the low side current sense here. This concoction of bits is the minus 5 volt generator or low impedance driver circuit, and an LM337L giving me the minus 5 volt supply. So that's they're the basic changes and additions. I have put a simple resistor on the output there. It's currently 330 ohm. That's serving as the minimum load, and that's sitting before the current shunt. So current drawn by this resistor is not being sensed by this current shunt here. A couple of changes worth noting on here. Because of this design here, and now having input an input amp instead of just a simple resistor divider, I now no longer need the buffer amp, the buffer op amp, which used to be here, to buffer the analog to digital converter. Because the output of this amplifier here is low impedance, relatively speaking low impedance. So the output of that simply is fed through the 4053 switch and directly into the ADC. That's negated the need for that second buffer. So that's removed a component, which is fantastic. This chip here is an LT1013, same as this chip, so I haven't increased the bill of materials on the project either. So that's what it's currently looks like. Let me just get this back on. Okay, so with the supply on, I'm just going to, right there, there's the trusty meter, Agilent meter, strapped to the output of the supply. I've just powered it up, so there's nothing coming out of it at the moment, and you can see what's coming out is 59 microvolts, or 58, 59 microvolts, so very, very low. If you recall before, and I haven't got a load on of it at the moment. I can place a load on it. If I place a load which is there, it lowers it a little bit further still. It's a very low impedance load. It's that halogen light bulb just here. But even without that load, it's sitting there at 56 microvolts. Now from software control, let me just initialize this. So what I'm going to do is set the output to 6 volts. There you go, and look at the result on the meter. It's 6 volts dead. You notice here this trimmer. Excuse me. Let's just get this. You notice here this trimmer. So in this prototype, I don't have that PWM circuit actually driving the trim. This is actually, I've just got it as a potentiometer here. So if you have a look at the voltage out, you can see you set a midpoint voltage. I think I set this on 4 volts. So if I just set this back to 4 volts, and then trim that to read exactly, you can see that it's quite, gives you fairly good control. That's down to 100 microvolts. There we go. So 4 volts. And obviously in the future this will be software controlled, and it'll be you set it up once and hopefully leave it. I think the because it's swinging effectively 10 volts across that potentiometer, or it will do with that servo, the PWM servo that we've created. It doesn't have to be that stable or that accurate. A lot of the error is taken out by the divide by 10,000, or the potential divider for 10,000. Okay, so there you can see the output. I'll just show you some of the settings. So that's 4 volts. If I set the maximum voltage you can set this to in its current times 2 gain is 8.1 volts. So you can see there 8.1 volts. And what's really, really important, actually let me just trim that up, just for the sake of being tidy. There we go. All right. So that's at one end of the scale, and obviously any linearity errors are going to come across the band. So the important thing now is it's 8.1 volts, and I'm going to drive that into the halogen lamp. And if you just look at the regulated output, bear in mind now that this is the circuit with the difference amp on the front end, and actually the way this is wired. If you just get here, just so you can see. So what you've got here is these black wires twisted around this blue and brown. The blue and brown are obviously the output, and these black wires are the sense lines. So these are the 2 lines that are effectively going to the input of that difference amp, and they're soldered together right on the back here. And this red and this green here are the actual Agilent meters. So I'm measuring the output voltage right at that point there. So if you look at the voltage output. That's with no load. If I place a load on it, you'll see this halogen bulb light. But if I place a load on that, you can see what the output regulation is now like. It's absolutely bang on. That's going from 0 to peaks at 4 amps. The regulator kicks in, and then it drops, as the filament warms, it drops to 2.5 amps. And you can see there that the regulator's loading really nicely now. The mains transformer I'm using can't quite deliver the current that I need at this point in time, so I'm just going to drop this down to 6 volts, and I'm going to put a second load on it. So there's actually this will attempt to deliver a little over 5 amps. I'm just going to set it to 6 amps, and again you'll see that you should see the output load regulation. If I can get on there we go. Absolutely bang on 6 volts still. So it's working really, really nicely. I do have actually a proper programmable load, and I will get around to speccing this at some point, but for now the lamps really do what I need them to do. The other part of the implementation was the current sense. It's not as accurate as any of the meters. It is a little bit off. I'm putting that down to the current shunt. It's only rated at 1%, and I'm going to work on implementing a software calibration scheme for that. So that's something I need to work on. But the main thing, I'm not sure how well this will work. The main thing on screen, you can see this is the software that you've seen before. So you can see the current output here being monitored, and as I put the load on it, you can see it there. The important thing to note is that it beautifully drops down to 0. There's a tiny little bit in there, and again on the voltage, if I turn the output off, everything's down to 0. So as far as I'm concerned now, I'm pretty comfortable that everything's working as it should. Everything's stable. Nothing untoward or unexpected is happening. The circuit seems to be functioning really, really well. All right, that's it for now. I'm currently in the process of designing a PCB for it. Yeah, it's a nightmare. There's lots and lots and lots and lots to do, so I shall persist on that. That's it so far. That's where the current shunts go. I'm actually in the PCB design for now. I might change my mind on this, but because I'm aiming for it to work with 8 amps, I've actually doubled up on the output devices and also doubled up on the current shunts as options. You don't necessarily have to put them in there, but I figured I'll aim to put that in there first and see how we go. I've also put the output protection, put a fuse on, and so on and so forth. So that's it, work in progress. I'll carry on now. The circuit I've got is final. This is what I'm publishing in this blog post, so have a look at it, see what you think. If you like what you see, post in the comments or hit the like button or anything like that. All right, thanks for watching. Bye-bye.